Okay, great. Well, today we're going to try to wrap things up. You guys have actually, and Zaid, yes, and Zaid's coming right now. So we've actually done some of this already, though we haven't talked about it explicitly. So the goal today is we're going to talk about heat pumps, we're going to talk about refrigerators, and we're going to talk about the second law of thermodynamics, which we've been avoiding up to this point. I think somebody, I think it was Isaac, maybe asked about it a little while ago, and I said, "Oh, we'll get to it eventually." Well, it's eventually because we're finishing today, so we need to make sure to touch on it and cover it before we wrap things up. So yeah, we'll do our best to get through this. All the notes are in the notes packet if you want to follow along, but obviously we'll be talking through it as we go. Now, all of these things pretty much that we talk about today are going to be in association with what you've been working on for the last couple of days. Those cycles and looking at the work and the heat and the change in internal energy, right? That's really the big idea of this unit, is being able to make the connections between the thermal processes that we talked about, the conduction, the convection, the radiation, being able to make connections with the kinetic theory of the gases and why are these things actually happening the way they are. This unit is really good about just kind of taking everything and putting it all together. I mean, you have a pretty good guess of what you're going to see on the AP exam. I'd say you've got a 50% chance of seeing just a PV diagram, just like the ones that we've been working on for the last couple of days and working through it. And then a 50% chance of something else, but even better than 50% chance, I think. It's almost guaranteed that you're going to see one of these PV diagrams. So let's start with the heat engine. Okay, so a heat engine is quite simple. It's quite straightforward. All right, the basic idea of a heat engine is we start with a place that has extra internal energy. So we define it as being hot because it has more internal energy, therefore it has higher temperature. Because it's hot, it should naturally flow to a place that is cold. So we have hot that flows towards the cold. Somewhere in between, we put in our heat engine. All right. Now the heat engine then uses that heat somehow to create work. And we're not going to worry too much about the mechanics of how it's turning heat into work, though we may see that in some of the examples as we move along. There's a whole bunch of different ways to do this. You know, the typical example is your car engine, right? In the car engine works because you've got fuel in there. You spark the fuel. That's the whole point of you've got these pistons inside the car. You spark the gas, it ignites the gas, causes the gas to increase in its volume. It then that causes the piston to go up, so the gas is doing work, and then you do work on the gas, causing it to compress, and it's one of those cycles that you've been seeing in your homework. And so that's what's happening in the engine over and over and over again. It has all these pistons that are moving up and down and doing those cycles like you see. And it's basically this heat pump, is that we got something that's hot, it's going down to cold, and we're hoping to get work out of it. We're hoping that the pistons are going to move, which is then going to cause the wheels to be able to turn, right? Obviously, there's a lot more mechanical stuff going on there, but that's the basic idea, is that we get those pistons moving due to the thermodynamics. We see this in jet engines as well, a similar process. We see it in the human body, right? The human body as well tries to take in energy, right? And then it tries to use that energy to do work, to move around, to think, to whatever else you do. So those things are kind of examples of these heat engines that we're talking about, using an engine to take heat and create work. All right. Now, one of the things that was mentioned last class was the idea of efficiency of an engine. Okay. Well, if it's a heat engine, well, you know what efficiency is, right? Efficiency is work out divided by energy in, right? That's what efficiency is. What do you get out? The desired stuff out divided by what you put into it. And in this case, what's coming in is that heat flow from the hot source. That's what's coming in. The desired output is the work. That's what we're hoping to get out. So when we say efficiency of a heat engine, what we're talking about is the thing we get out, the desired outcome, divided by what's going in. So work divided by the heat in. And my fat head's in the way, I'm sorry. Now, we can actually define this just in terms of the heat. If we know the heat in and the heat out, we can actually do this as well. How would I do that? How could I rewrite this so that it just has heat, no work? Assuming no energy lost to the surroundings in our perfect physics world here, physics land.
What about, we can say that work is delta U minus Q?
Okay, so using first law of thermodynamics, we could say work equals delta U minus Q. Yep, even simpler though, there's something else that we can do in this scenario.
What, negative P delta V?
We could do that as well, but that's going to bring in P and V. Is there anything we can do just with the variables that we have? These are great ideas. I love the connections. Just not where I'm trying to go right now. Maybe on some other question. What has to be true about the energy? I've got energy coming in. I've got energy going out. If it comes in, it's got to go out, right? But if it doesn't come out here, then it means it must be going out as work, assuming that we're not losing anything. Yes, Sophia.
Q in minus the QC, the Q that goes out.
Yeah, so work is going to be equal to the difference in our heats, right? If I've got 10 joules coming in and I got 3 joules going out, assuming nothing's lost, I must be getting 7 joules of work. And so we can rewrite the work as hot minus cold. So our efficiency can also be this.
Shouldn't it be cold minus hot?
Sorry?
I mean, isn't it cold minus hot instead of hot minus cold?
Good question. Good question. In this scenario, I see what you're coming at. In this scenario, we're saying the work that's coming out. So this is not the same W that we see in our delta U equals W plus Q, right? In this formula, work is what's being done to the gas, right? Yeah, no, you can't see that. Okay, in this situation, the work that we're talking about is what we're actually getting out of the system. And this is why some textbooks or some courses will automatically define work as being work that comes out, because then there's no difference between the work that we're talking about here and the work that we're talking about here in the first law of thermodynamics. Remember that the plus and minus is just direction, right? It's considering which direction the work is doing, what's doing work on what. So in this, we do have to make that separation due to the way that AP has asked us to make the convention here. That here work is positive when we're doing work on the system. In this situation, the work is positive if we're getting work out. And that's why, Whitney, we are going to do H minus C, because it's actually the opposite, right? It's the opposite of what we expect there.
Okay, thank you.
That was a great question. I'm glad that you're thinking about things like that. Other questions? All right, one last thing, and then we'll do a quick example, and we'll move on to a different type of engine, a specific type of engine. One of the things to recognize is just like when you did conservation of energy. I don't know if you remember back in the day when you did conservation of energy, anytime that we had like energy efficiency or anything like that, or we were talking about conservation of energy in general, you could divide everything by time, and then you'd have kind of a conservation of power or a conservation of rate of energy change. I don't know how extensively you guys did that. I know some courses go really deeply into that connection with the power and the energy, and some do less. But the idea is that here, instead of doing work over heat, you can change those both into a rate. And so you can say how much work per time are you getting and how much heat per time, or that heat rate, right? That's significant because that's the formula that we have in our conduction, right? It's Q over T. And that's what we use when we do the heat transfer in the conduction equation. And so just recognize that we usually define efficiency in terms of the work and the heat, but we can also use that equation with the rate of work being done and the rate of heat being transferred out. Okay. All right. Why don't you try example number 17 in the packet? I think that you can probably do this one on your own, so I'll give you a couple of minutes and then we'll share out. I'll read it off for those that don't have it in front of you. It basically says a simple engine does 350 joules of work and expels 750 joules of energy. The question is, what is the efficiency? So once again, it does 350 joules of work and it expels 750 joules of energy. What is the efficiency? So I'll give you 2 minutes. Go ahead, work through that, and then we'll move on. All right, so for anybody watching from home, I'm sorry I forgot to turn the camera back on. So just a quick summary of what we did in the last couple of minutes. First off, we talked about the answer to the question, which what would make the most efficient energy, heat engine. First, we said if no energy went out the bottom, right? If no energy went out the bottom, it was all going from the hot into the work, that would be the most efficient. Unfortunately, if that were the case, the heat wouldn't flow because it needs to go from high to low. It wouldn't naturally flow anymore. The second thing was if you can reduce friction and outside heat loss, because that's a realistic thing. Anything that gets lost through friction or through just radiation to the outside, you're not going to get as work. That counts as part of that heat flow out. So that kind of connects with all that. And that would be the most efficient. Now, then we went into the Carnot engine. The Carnot engine is a very specific type of heat engine that follows a very specific process, the most ideal process. All right. And in this process, we start at a point, we undergo isothermal expansion. So it goes through an isotherm here. After isothermal expansion, it then goes through adiabatic expansion, which then changes the temperature, but doesn't lose any heat. And then we go from we do an isothermal compression, which again follows an isotherm, comes back up here, and then it undergoes adiabatic compression, which then takes it back up to the top. And so that is going to give us the most ideal engine possible because it follows what we call reversible, for the most part, processes, except for which means that we're not losing significant energy during those processes. The isotherms, we keep at the same temperature all the way, which means the internal energy stays the same. And then with the adiabatic, we're doing it so quickly that really there isn't time for heat to be lost. And so this gives us a very ideal situation. The formula up here, this is the efficiency of a Carnot engine. Instead of doing it in terms of heat, which we could, we can also write it in terms of temperature. And we didn't go into a derivation for that. We just said, okay, this is connected with the internal energies and heat loss and things like that. This is probably worth knowing and memorizing. This is not really an understanding thing, just knowing that a Carnot engine can be done with respect to the temperatures, not just the heat. Though you can do it with heat still. That still applies. Okay. Everybody should be coming back. Right now they're talking about what would be the most efficient Carnot engine. So we already said Carnot is ideal for an engine, but okay, what would then make the most efficient Carnot engine? All right. And here they come. All right, guys, what'd you come up with? What would be the most efficient Carnot engine? Dory.
Okay, I don't know about how this could actually work in real life, but
Good. Ideal things don't work in real life.
okay, cool. Akrit, Whitney, and I were talking about how if you make the abiotic process as long or as large as possible, then that's going to increase the area of the graph, which means it's going to increase the work. But since work isn't lost in that process, or Q isn't lost in that process, that's going to allow you to generate the most work in the end and create the most efficient engine.
Okay. All right. Anybody else like those ideas?
The thing is, but you can also use the temperature thing for a Carnot engine, and then you'd want your isothermal to be the largest because temperature doesn't change in an isothermal reaction or process, right? So
She's typing in the chat. Eating? Oh, he's not anymore. Well, bye-bye. Oh, he's here. Okay, Mr. Bywater, you're back. You're still muted, though.
Yeah,
You're muted, good sir. All right.
It kicked me out, and actually I was kicked out of my computer. So when I turned the computer back on, it logged me back into Zoom, but I was not logged into my computer. So I could hear you guys, but I couldn't do anything. All right. So yes, obviously the tech gods hate me today. That's all right. Bring it on. Okay. So sorry, Isaac, what were you saying about temperature? I think I had lost about halfway.
you gave us the temperature. You said you can use temperature to find efficiency instead of heat. But if that's the case, then the isothermal expansion would want to be greater because the temperature isn't changing there. And you want the TC valuable to be the least. So I'm not sure how you can say that both abiotic and isothermal should be the greatest.
Okay.
They're both-
So yeah, so thinking about this, and this is actually going to connect into what was said earlier. This is what we're interested in looking at, right? Really, the key is to make this change as big as possible. Now, if you look at it mathematically, so take off our science caps just for a minute and look at it mathematically, because sometimes math, well, all the time, math helps us understand what's going on a little bit better as far as the science goes. If I make TC 0, what happens to this equation?
It's 1.
Becomes 100% efficient, right? This is connected with what you guys were saying earlier with the heat. If I can make that QC 0, if nothing is going out the bottom, then it makes it as efficient as it possibly could be. The only way for that temperature C to stay at 0 is if nothing goes out down there. And so the amount of heat coming in is the amount of heat going out into the work. And so if I can come up with, that's one of the reasons why this idea of absolute 0 is so enticing, because if we could come up with some way to efficiently make something at 0 degrees Kelvin, we could essentially create the most efficient Carnot engine or engine in general, right? Now, the other end of the spectrum is also true. What would happen? I think most of you guys have done some limits in mathematics. What would happen as TH approaches infinity if we give it lots and lots, if we make that isotherm very, very high?
Then we will have also 100%.
You also get 100%, right? As TH approaches infinity, whatever you're subtracting off here is no longer important. So the larger you can get this temperature, again, the more efficient you're going to be. 1,000,000 minus 200 degrees is not going to make a difference. It's still pretty dang close to 1,000,000. And so you're still going to get a 100% or very close to it efficiency. Of course, now the problem is getting something to that temperature means that it's going to be radiating off a lot of energy. So how do you get it to not radiate off all that energy? So you can see, what engineers are looking at when they try to create more efficient engines. They're trying to either decrease the temperature or increase the temperature in the hopes that that is going to create a more efficient engine. Of course, the other idea is that you take out, as we mentioned before, all the other frictional aspects, the friction, the radiation, you insulate it, all these other things that would allow you not to be losing energy as you go through. Okay, questions? Sophia.
So you wouldn't want any heat transfer at all?
That then becomes the issue, right? Is because we have to have heat transfer during the isothermal processes, right? If there's no heat transfer, then it can't be isothermal. It needs either heat coming in to maintain that temperature as it expands, or it needs heat going out to maintain that temperature as it compresses. But if we can get those to be as close as possible so that heat in and heat out are the same, then we're in a more ideal situation. But you're right, we can't avoid the heat in and out. It's more of a sense of being able to balance that heat in and out, or making our output so large that it doesn't matter. Remember, again, it's about efficiency, right? If I can get 1,000,000 joules out, it doesn't matter if I lose 1,000 joules of energy in the process. If I'm only getting 2,000 joules out, then losing 100 joules is a big deal, right? So it's all about proportions. It's all about ratio. It's all about efficiency. So if I can get a heck of a lot of energy out, it really doesn't matter what I lose in the process. Or the exchanges don't get so much out, but really reduce that loss. It's a good thing to think about. Awesome. Anybody else?
Mr. Bywater, I still don't understand why, if we can get 0 Kelvin that would increase efficiency.
If TC, that's this temperature, is 0, this equation now becomes efficiency equals hot temperature minus 0 over hot temperature. Right? Which means the math then says that this minus that is still hot temperature. And so hot temperature divided by hot temperature is 100%. That's 100% efficiency. So that's what the mathematics is saying.
Okay.
As far as conceptually, remember when we talked about the heat engine at the beginning, we said ideally we don't want any heat going out the bottom, right? We want heat coming in, we want work going out, we want nothing going out at the bottom. Unfortunately, if we have that low, realistically, if we have that low of a temperature, you're going to get heat going in unless we have some way of maintaining it at 0. Yes, Isaac, that is true.
Okay, thank you.
Okay. This seems like a good place to take a break. When you come back in 2 or 3 minutes, we'll talk about heat pumps. There's really not a lot to talk about there. It's just introducing the idea. You've done most of the conceptual work already, so we'll do that. And then we'll talk about entropy, and then we be done. So go ahead, take 2 or 3 minutes, have a break. Somebody remind me to turn back on the recorder when we come back, because I forgot last time. Thank you. Ago, and I still would have forgotten. I just get so excited. You know, I get so excited to talk about physics that I don't remember all those technical details. I'll be so happy when I don't have to worry about it anymore. We can just chat. All right. All right. Here we go. So just really quick on the refrigerator, the heat pump. Okay, so a refrigerator heat pump basically works opposite a heat engine, right? A heat engine tries to take heat from a heat source and get work out of it. Okay, a refrigerator does the opposite, right? It tries to take the hot air from inside your fridge and kick it out to make it colder. And that, in some ways, that is difficult to kind of conceptualize because we realize that it doesn't work that way, right? You can't take something from a cold place and get it to move to a hot place. Well, you can't do it unless you do work. That is, of course, why your refrigerator has to be plugged in, because the refrigerator needs energy. It needs work to be able to complete that process. We're not going to go deeply into that process, of course. You could always do that if you have an interest in large appliances like refrigerators. But right now, what we want to focus on, of course, is just the physics of what's going on there. So we have our cold area. This is the inside of your fridge, which then you're trying to take heat out of that cold place. You have your pump, which is replacing the engine, because instead of work coming in, instead of work going out, work's coming in. That's plugged into your electrical thing that'll do some mechanical work there. Work comes in, which then allows more heat to be shot out towards the hot end, which is why the back of your refrigerator often is warm back there, because it's trying to radiate that energy out to the outside. Your house essentially is a large refrigerator, right? That's the point of an AC unit. The point of an AC unit is to take the heat. I know what we feel is the cold air coming out, but really what happens is that air goes in, it takes the heat out of it by doing work on it, and then it spits out hot air somewhere else. That energy has to radiate out somewhere. And that's how a AC unit works. It can't just magically make the air cold. All right, so that's the basic idea of it. We don't normally talk about the efficiency of a refrigerator, of a heat pump, we talk about something called the coefficient of performance. And so really what we want to know when we're looking at a refrigerator is how much work does it take in order to get this stuff out. I really don't care about what's being spat out in the end, right? The stuff that's going outside of my refrigerator, the stuff that's going out into the environment outside my house, that I don't, I mean, obviously there may be environmental concerns and things like that, but as far as the cooling process, I don't care how much heat gets spat out. What I care about is, can I cool off my refrigerator? Can I cool off my house? And so that's why we define this coefficient of performance, because efficiency isn't the deal. Now, of course, you know, engineers are going to look at efficiency because in the end, we do care about how much work it takes because that's more electricity. But in the end, what we care about is this coefficient of performance, which is simply how much heat is getting pulled out compared to how much work do I have to do? How much electricity does it take to get this much energy out? That's what I'm interested in when I'm talking about a heat pump. And so we don't talk about efficiency. We talk this coefficient of performance. Similar to before, we can change that work. That work in an ideal isolated system is still going to be the difference between QH and QC. So we can rewrite this just like we did before. In terms of the heat. And that's really, sorry, I'll move, there we go. That's really all we need to do in terms of the refrigerators, is just recognize conceptually that it's exactly like a heat pump. We're just, a heat engine. We're just running it in reverse. Instead of putting work in, instead of getting work out from putting heat in, we're now doing the opposite. We're putting work in and getting heat out. We're trying to get the heat out. If you look at a PV diagram, it would look exactly the same, except in the opposite order. We could create a Carnot heat pump, right? We could very easily create a Carnot heat pump by, instead of doing this process of isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, going in the opposite direction, doing an adiabatic compression, isothermal compression. That would all be expansions, wouldn't it? So adiabatic expansion, isothermal expansion, adiabatic compression, isothermal compression. So if we were to do it in the opposite direction, it would give us a Carnot heat pump, what we would consider to be the most efficient heat pump rather than a heat engine. Questions? I want you to take 30 seconds to check your formula packet. Out of the formulas that we've talked about today, what is in there? You see any of those in there? No. Is efficiency in unit 1? Just general efficiency? When you did mechanics last year, you talked about regular efficiency, right? No, you didn't do anything with efficiency last year? Oh. Okay, so I guess it wasn't there either. All right, so efficiency is not in your formula packet. And yet it is something that could and is likely to show up on the AP exam. So this is one of those conceptual things, kind of like how they don't give you everything in mechanics because they expect you to know that acceleration is a change in velocity over time, that type of thing. Velocity is a change in displacement over time. They expect you to know some things kind of as definition or understanding things. This is one of those. Efficiency is what you get out divided by what you had to put into it. Okay. And so you want to make sure that you have that understanding so that when you have a heat engine, that you'll know that efficiency is work over heat coming in, right? If you understand that, you should be able to create the efficiency even without having that equation. You should be able to recognize, because of our talks in thermodynamics, that work is the change in the heat. And so you can get the second equation. If you know that, then you need to make the connection with the Carnot engine, right? That in a Carnot engine, the most ideal engine, because of all those adiabatic isothermal processes, we can use the temperatures instead of the heats. It's the same exact formula, except instead of Q, it's using the temperatures. Okay. And then last of all, when we talk about the heat pumps, we should be able to make the connection that what we care about is what I'm getting out, dependent on how much work is required to do that process. And so those three things are not on the AP exam, and yet they can ask those questions because efficiency is a concept. It's an idea of in versus out. Are we getting what we want? Okay. Questions? Camilla.
For the PV diagrams, to find internal energy, we needed to use U, internal energy equals 3/2 nRT, but that's not on the equation sheet. So would we?
Correct. That's one of those things that I was mentioning at the very, very beginning of class, that in the homework you might see that, but you won't be required to use that on the AP exam.
Okay.
The only reason it's in the homework is because I'm giving you old AP questions. And I'm not, the problem is a lot of the recent ones, I'm not allowed to give you in a free format. I can only give you those questions. A lot of them, I can only, the more recent ones, I can only give you in a lockdown browser scenario, because so many teachers use them for tests and exams and things like that. And so there's a lot that I'm not allowed to give you. And so I'm trying to give you AP style questions, which means I have to dig a little bit deeper, a little bit later, earlier. And those, before they had the syllabus change, some of those things were in there. And so, yes, I'm sorry. When you do your homework, you might see that formula, but it will not be on our celebration, and it will not be on the AP exam. Same thing with those, the CP and the CT that were in the first two questions on the homework I posted last night. You don't need to know about those. Those won't be on there.
Okay, thank you.
Yep. All right, anything else? We got entropy. Entropy might explain the issues I've been having today. The second law of thermodynamics, the one that we haven't talked about yet, the second law of thermodynamics basically says that all spontaneous processes, all processes that just happen, that don't need extra energy or extra work or extra things to make them happen, all spontaneous processes in an isolated system, so not affected by anything outside. Okay, that's the idea of all this. All spontaneous processes in an isolated system will result in increased entropy. Okay, and don't worry, I'm gonna explain what entropy is. For those that, I think if you've been in chemistry, you probably have talked about it. Anybody talked about entropy before? So a couple of you have heard of entropy. That's okay, we're gonna talk about it right now. A couple more. All right, awesome. And then of course, some of you that I don't see your hands being raised, so I don't know. But all right, so entropy is a measure of the disorder of a system, how chaotic it is. Okay, so I said that this is very likely a great example of what has been happening to me today is that the universe tends towards disorder. Me getting kicked out and freezing up and all this disorder. That's how the universe works. So maybe the universe isn't angry at me. It's just that's the way things are. The universe tends toward disorder. And you've seen this in lots and lots and lots of scenarios, right? We've been talking about, for example, convection, right? Convection happens when you have a high pressure area and a low pressure area. Right? In a high pressure area, or we talked about it in terms of density, but that's because if the particles are more packed together, they're more organized. They don't like that. They tend to move into less organized areas. Goes from this high concentration to the low concentration. If you've ever taken a drop of food coloring and dropped it into a cup of water, you notice that the food coloring doesn't just sit there in a concentrated dot. It eventually spreads out throughout the water because the universe tends to disorder. It doesn't like having everything in this organized little compact place. That's not the way that the universe works. Even looking at the universe as a whole, the universe is not the same everywhere. The universe is different all over. Even when we talk about the Big Bang and how everything was concentrated in this little point and explodes out from there, the universe was not in this nicely organized thing. The universe was in disorder, and it continues to become more disorderly with packets here and packets there, and it's not evenly distributed over the whole universe. It tends towards disorder. Everything does. Thinking about, let's see. So let's see. All right. So I should talk about the interpretations of this second law, because you'll often hear the second law phrased in different ways, depending on how people want to use it at the time. All of these connect back to that idea of the universe tends towards disorder, or everything will result in increased entropy, because entropy is a measure of the disorder. And you may ask, well, how the heck do we put a number on disorder? How do we put a number on how chaotic something is? Well, normally we won't talk about a specific value for disorder. We will talk about a change in the value of disorder. And so it'll usually be a delta S, because what we're interested in is the change. And does something go from more orderly to less orderly, or does it go the opposite direction? Absolute entropy is not something that we're even going to try to touch. So the one interpretation of this is the Kelvin-Planck interpretation. You've probably heard both of those names before. Kelvin, Lord Kelvin, the dude that did the temperature scale, and Planck, who did a lot of things with modern physics, atomic physics, things like that, especially with photons and energy packets. Their interpretation basically is that it is impossible to create a heat engine that completely converts heat into work. They were concerned with that type of mechanical engine work. So they basically said it's impossible to create a heat engine that completely converts heat into work. The reason being is that that's not natural. The heat has to flow from hot to cold. If you get it all out in work, then there's no hot to cold flow there. That's not how nature works. Nature doesn't allow us to go from a very concentrated area to being able to focus it even more as work. That would not be decreasing that would not be increasing entropy. That would actually decrease it. That would make things more organized, to put it in a useful way like that. Okay, so that's Kelvin Planck. I don't think that the names are super important. There's not going to be a multiple choice question asking about the Kelvin Planck or the Clausius interpretation. Okay, I put the names on there just because you may see those names in a textbook or something like that. But otherwise, it's not important. Understand that one interpretation is it's impossible to create a heat engine with 100% efficiency. Okay. The second one is the Clausius interpretation, which says that heat flows spontaneously from hot to cold, but not the other way. Okay. Pressure and particles, it kind of makes sense to think about particles going from a concentrated area to a less concentrated area. Heat is a little bit harder. We have talked about the idea of temperature and things moving faster when they run into something slower, energy transfer. So we can see that heat transfer going. But basically, he said it is natural for heat to flow from hot to cold, not the other way around. Obviously, the thing there is that then the heat pump that we talked about in the second half, the heat pump requires work in order for this to happen, to go the opposite direction. We can go the opposite direction. We just have to bring in energy from the outside. We can decrease entropy. It just takes energy to do it. It's not natural. So that's basic. So the first one talks about the heat engine and says, yeah, we can go from hot to cold, but we can't get everything out. The second one says, okay, well, it doesn't naturally go from cold to hot, or from cold to hot. But if we put energy into it, we can get that to go in the opposite direction. And then the other one is basically what we've already said, which is that a system undergoing spontaneous change, something doing something on its own, will always cause an increase, or at best, no change. It's possible to have a reversible process that has no change in the entropy of the system. It will always move to a state of greater disorder. And that's essentially the same as the definition that we gave in the beginning. So I want you to think about this. Yeah, I got time. You got water, just some liquid water, glass of liquid water, and you want to make it ice. How does the second law of thermodynamics apply? And specifically, how does entropy apply? And I want you to think deep at the molecular level, right? That's what we've been doing for a lot of this unit, was digging in deep and not just looking at the big picture, but also digging in deep and looking at the molecules. All right, so I'll repeat that one more time, and then I'm going to send you out into breakout rooms to give you a couple minutes to kind of talk about and discuss this. All right, so once again, you've got liquid water. You are going to make it into ice. How does the second law of thermodynamics, and specifically entropy, how does that all fit into this scenario, especially on a molecular level? Okay, your rooms are ready. You can go. I'll see you in a couple minutes.
possible,
I
in
think
specifically entropy.
Mm.
So
I
don't
think
know.
you'd have to put it in a container in which the surrounding is colder than the water, so that the water will give heat to the surroundings, and then it will become colder and it'll become ice.
Mhm. Yeah, because it's not natural for something to go, because obviously water has more entropy than ice does. So then you would have to put work in to create the ice. But then I guess you can just use like a heat pump, like a Carnot heat pump to generate the
Yeah.
cold, right?
Yeah, I don't really understand exactly what he's asking, but
I don't really understand how like you can use disorder to predict it. Maybe that's something I'm missing.
It's kind of a hard concept, but basically entropy you can use to determine the direction of different chemical processes, because like
You guys done?
Yeah, I've got a pretty good answer.
I'm excited to hear your pretty good answer there, Zaid.
Yeah? Okay. We'll see how good it is, I guess.
All right. Go ahead, Zaid, share with us.
Yeah, so we thought this was just straightforward. We correlate disorder with like the movement of the molecules, how much they move. And so in water's a liquid, so they're allowed to move more freely. And Sophia mentioned an interesting point where if, like, let's say we're talking about water in room temperature, then some water molecules would be moving faster than others, so that'd be more disorder as well. But in ice, it's just a solid block of ice, and they kind of form like a lattice of H2O molecules, and they more like vibrate. So it's less disorder than water in its liquid form. So when you convert water, when water goes from liquid form to a solid form, from water to ice, then entropy decreases. That's what we said.
Okay, cool. Is that allowed to happen? We allowed to decrease entropy?
As long as you have work being done.
Okay, so as long as it's not an isolated system, right? As long as you have, Sophia mentioned the work coming in from outside, right? So we put it in the freezer. Let's see if we can expand out a little bit, because we said the universe has to tend to disorder. So we know that the water itself, I think that's a great explanation of why the water is going to have decreased entropy. Two great reasons. One being because the molecules are fixed in place now. They're not moving around quite as much. And then also the idea, when we talked about before, we talked about the curve of the kinetic energy versus temperature. Remember that at lower temperatures, the curve looks something like this. And at higher temperatures, it looks something like that. which one has more variation and more variability? Well, it's the higher temperatures, right? So higher temperatures will always have more disorder, okay, in this scenario. All right. So we're going from that water, which has a significant amount of disorder, to this ice. So it's becoming more orderly. Okay. Sophia mentioned the work, right? Obviously, that's because we're inside the freezer and it requires some energy to do that. We're having to bring some energy in to cause that process to happen. Somewhere down the line, you do that. And what are you doing? Well, when you do that work, energy is being dissipated out into the environment, right? So if you consider the outside as well, remember the heat that's going out is greater than the heat that we're actually taking out of the ice because of the work coming in. And so the molecules in the air now are going to be more disorderly, right? They're going to have greater disorder than the amount of order that we were able to impose on that water, on that ice. And so the universe is still in balance because the universe is tending towards disorder, even though we're able to increase the order of our water into ice. All right, so I think it's good. I like the explanation of talking specifically about the water and ice, but I also want us then to expand a little bit more and say, okay, how does this fit into the big picture of things in which the universe has to go towards disorder? How does that eventually happen? Well, heat's being spat out. Awesome. There's no formula in the formula packet for entropy. Generally, if we put a number with it, we say that entropy, or S, is equal to Q over T. Okay, the amount of heat, that's actually the change in entropy. Delta S is equal to Q over T. So the amount of heat that was transferred divided by the temperature at which the heat transfer is made. That obviously becomes a little bit difficult if temperatures are changing and things like that. It requires, for the most part, some calculus. Requires some calculus. And so that was the last thing I wanted to mention. Thank you, Krisha. But yeah, I just wanted to make sure that I mentioned that, even though it's unlikely that you'll see any calculation with that. It's all just conceptual. Okay, that's it. I'm done. We're done. Thanks.
Have a good day.
You got questions? I'll hang
Thanks,
out.
Bywater.
Have a nice weekend, Mr. Bywater.
Have a good weekend.
Thank you, Mr. Bywater.
Bywater, can I ask a question?
Of course.
So I was wondering, for the PV diagrams, for the adiabatic process. Sorry, my mic is. I'll speak louder. For the adiabatic process, does volume decrease?
Adiabatic depends. Which way are you going? Adiabatic just means no heat goes in or out. You can go one way or the other.
So is that with all of them?
Yes, yes, I should have been clear on that. Yes, all of those processes can go either way. You're right. I think maybe I made a mistake there, because every time I did it, I said, okay, let's look at the example of the gas expanding. And so we talked about isobaric expansion at the same pressure, but maybe I didn't necessarily say this can go back the other way. So yes, all four of those processes can go either way. That's why we had, with the Carnot engine, remember, we had isothermal expansion when it went that way down the curve. And then we had isothermal compression when it went the other direction of the curve. So yes, all of them can go both directions.
Oh, okay. Thank you. But it would always be negative, right? The sign wouldn't change.
The sign of what?
Or like, for example, would volume always be negative?
It'll depend, right? You have to look at the direction of the change, right? So we talked about the Carnot engine here earlier today, right? And so this one right here was adiabatic, going from there to there. And you can see that the volume increased. We moved to the right on our PV diagram. So in that case, delta V would be positive, right? The temperature decreased. So we'd say delta T decreased because it went from a higher temperature to lower temperature, but the volume increased. If I look at the other one, the adiabatic compression, it's going to be exactly the opposite, right? This one is going to go from here to, my drawing wasn't very good. From here to here, the volume is decreasing and the pressure is, the temperature is increasing.
Oh, okay. I get
So
that.
yes, all of them, if you go the opposite direction from what we talked in class, all of the signs should be the opposite of what they were before.
Thank you.
Yes, I apologize. I should have been much, much clearer on that.
Thank
I
you.
even thought about that last class afterwards. I was like, I never really talked about the fact that it's both ways. So yeah, good questions.
Thank you.
I have a question about the PV diagram worksheet.
Okay.
On the third problem, I don't really know how to find the internal energy. It's the one.
Internal energy?
Yeah.
Is this the one from that I posted up yesterday, last class?
No, it's the one before.
Before? Okay, hold on just a second. Let me open it up.
It's the one with only variables.
Okay, give me just a second to find it. All right, so the simple thermodynamic processes.
Yeah.
Okay, PV diagrams, number 3, you said?
Yeah. At point B.
B?
Yeah.
Okay, so the volume expands to 4 times the original value under an isobaric process.
Or
Okay.
no, from at point B, what the internal energy is.
Thank you, Mr. Bywater. Bye.
That one, you're going to need to use that internal energy formula, the one that we mentioned at the beginning. It was we talked about it in class, but it's not on the AP packet.
The 3/2 nRT.
Yep, the delta U equal, because if you have the temperature, you can get that. You can often find a change in internal energy without that, but to find the actual internal energy at that point is difficult to do without a formula for U.
I tried that, but I think I got a different value than what was on the answer key.
Using the 3/2 nRT.
Yeah. This pressure is 3 T0, and then temperature is 3 T0, right? And so then
And V is V0. And the temperature, what do you have for temperature there?
3 T0.
Okay. Yeah.
Wait, what was the answer? Is it 9/2?
I'm just double checking. Yeah, 4.5.
Oh, okay, never mind. Okay, it makes sense now.
Okay, lovely.
Yeah, I don't know what I was doing. Okay. Thank you.
Yeah, you're welcome. Yeah, just keep in mind, you may need that on this worksheet, on any of the worksheets, but you won't see that specific thing. The other idea is you will see being able to make relationships between heat and work and internal energy, stuff like that, that you will need. But yeah, specifically that equation won't come up.
Okay. Yeah. I don't know what I was doing wrong. I just had to like use ideal gas law in this other one. Yeah.
We'll blame it on entropy.
Okay. Thank you.
All right, see you later.